Hi everyone, welcome to the ECCV workshop on compositional and multimodal perception. I'm Jingwei from Stanford University. Today I'm introducing our Action Genome, a video database bridging human actions and human object relationships. Let's consider an example of someone sitting down on a sofa. So what are the cues for recognizing this action? In each frame, we can spot a person and a sofa. We know where they are. We also understand their relationships and the changes of the relationships across time. Then we know that in this short video clip, the person has performed the action sitting down on a sofa. So how can an intelligent agent leverage such decompositions for recognizing actions? We need a new representation, database, and algorithms. Here we introduce Action Genome, a representation decomposing actions into spatial temporal scene graphs. Action Genome is the first large-scale video database providing both action labels and spatial temporal scene graph labels. Action Genome is built upon the charades dataset, where the researchers have collected 9,848 daily life videos containing 157 classes of actions. We further provide the decompositions of these actions, including more than 476,000 bounding boxes of objects that humans interact with them in the videos, and 1.7 million human object relationship instances of three categories, including attention, spatial, and contact relationships. When annotating each video, we start from the labels provided by charades, which are action classes and temporal boundaries. We uniformly sample 5 frames from the time interval of each action. On each sampled frame, we localize all the interacted objects. Note that we are not necessarily labeling all objects appearing in the scene. We only label the currently interacted objects. We've neglected all objects that the person in the scene is not actively interacting with. We then annotate the pairwise human-object relationships. So then we can formulate the spatial temporal scene graphs. Let's see some statistics of the database. Here's the distribution of object occurrences. Most objects have at least 10,000 bounding boxes labeled. And here's a distribution of relationship occurrences. We have 3 types of relationships. First, attention relationships, which indicate if the person is looking at some objects or not. And second, contact relationships, which describe how a person contacts an object. For example, touching, holding, sitting on, etc. Third, spatial relationships. For example, in front of, behind, on the side of, beneath, etc. As we can see from the distribution, most relationships have at least 1,000 instances. Here's a weighted bipartite mapping between relationships to the objects. We found that contact, attention, and spatial relationships are involved with a wide variety of objects, such as touching and looking at and behind. Most objects, like door, are also involved in various relationships. But there are also a few objects and relationships that are exclusively involved in 1 or 2 relationships and objects, respectively. For example, writing on to paper or notebook. So we validated the action genome's action decomposition by studying the effect of simultaneously learning spatial temporal scene graphs and action recognition. we propose a method called scene graph feature banks to incorporate spatial temporal scene graphs into action recognition. So given if the model is given an input video, we first predict the scene graph of frames. These scene graphs are converted into feature representations, for example, a matrix of objects and relationships. We also extract short-term clip features using 3D CNN. Then we merge the features with feature bank operators to predict actions. There are more details in our paper published in ECCV2020. We validate this method on two tasks, action recognition and few-shot action recognition. In action recognition experiments, we show that grounding the components of actions, which are in our definition, which are the objects and human-object relationships, will improve the predictions of occurring actions. In few-shot action recognition experiments, with the additional knowledge of scene graphs, our method better generalizes to action classes with only a few training examples. Again, for more details, please see our paper. Here we show an example in our few-shot experiments. The ground truth action labels included in this video clip are as following: awakening in bed, lying on a bed, and snuggling with a pillow. The baseline method mistakenly predicts watching television in it, while our method captures the relationship changes between the person and objects. Thus, so for example, the changes between the person and pillow from holding to not contacting, then in the end, it successfully predicts awakening in bed. In order to promote progress on spatial temporal scene graph prediction in videos, we evaluate existing scene graph predictors on Action Genome as a benchmark. There are several future directions that Action Genome has already enabled. First, spatial temporal action localization. Previous methods or models in spatial temporal scene graph action localization usually only localize actors, but here with the Action Genome's annotations, you can not only localize the actors but also the interacted objects. Second, we can develop explainable action models. We are providing the decomposition annotations of actions, so specifically the objects and relationships, and then we can use that as frame level labels of attention for training and evaluating explainable action recognition models. Third, video generation from spatial temporal scene graphs. From our given structured video representations, can we synthesize videos from the spatial temporal scene graphs? For the data, please visit our Action Genome dataset. Thank you.